we've met. I don't think that you don't know who I am by now by the final exam. So I'm very, very happy to be working with you today. As I always say in my sessions, teaching at Queen's is one of my favorite places. I'm gonna begin today with the series part, and then tomorrow will be the multiple integral part. Everything that's before the midterm, I pre-recorded that for you. So I did what I would do in a session here, except it's pre-recorded for you, and I'm told by head office that it's already posted for you, so you can watch it. I'll show you what we did. I covered these topics. So partial derivatives, implicit linearization, differential. I crossed them as I covered them, just to make sure that I covered everything. And as a bonus, I solved a final from beginning to end. So the 2017 final. So I solved it from beginning to end, all the topics, everything, just to give you like a flow of one solution for an entire final covering everything. So all of these topics are already covered. They're already summarized. There's plenty of nice problems. Look, these are the problems that I did. I'm also going to post the notes that I worked on. So you'll have access to the video and you'll have access to my notes, everything. It's like our session now, except that it'll be it's already done and it's already there for you to watch. So in the live sessions, which are 4 hours today and 4 hours tomorrow, I want to focus on the series part and I want to focus on the multiple integrals part. If you have any questions about any of the parts, really, all you have to do is tell me in the Q&A, obviously, but if you're watching on video or if you have a question outside the live hours, by all means, send me an email, and you know me, right? I will do everything possible that to help you prepare, to help you understand, to help you get everything in order. Whatever you guys need, I'm here for you. So that's what we're gonna cover today. The notes for everything I write, as usual, as always, all these things I write will be made available to you on CourseCram at the course page tomorrow at the end of the session. And this session is recorded. The video of today will be available tomorrow. The video of tomorrow will be available on Tuesday. Welcome to 172 final exam session. I think 4 minutes is a long enough introduction, having met several times before. Let's begin. Right, so here we are. I'm gonna begin with series. I'm hoping to finish series today and then tomorrow to do multiple integrals. We are gonna have 2 breaks, about 15 to 20 minutes each, depending on how the flow of the session is. And the first break is in about an hour and a bit, so about 80 minutes, and then a break, and then about an hour and a bit, and then a break, and then, we finish the whole session. If there is anything, one final remark, you probably know this by now, but there are no more printed material for me. So CourseCram does not print the booklets or anything for me because I asked them honestly not to. I don't use them. I use my notes for the session. I use your final exams. I use like problems that I make up for everything. So since I'm not using them at all and they don't really serve a purpose except for your review, I've asked them like not to print them, to save some trees, to save some paper. It's you have access to them on the course page until your final exam. Right, so that's our story. Let's begin. So series, a very interesting topic, a very lively topic to say. So what's a series? A series is an infinite sum. So it's the sum from, let's say, n equals to 0. This is the starting n to infinity of some general term an. So a sub n, this would be the general term. This is where n starts. And clearly it just goes to infinity. So this would be a0 and then plus a1, then plus a2 plus until the end of time. So We call a series convergent. So a series converges. This means that this entire sum, so this means the sum from 0 to infinity, the entire sum until infinity of an, wherever it starts, is equal to just some fixed number L. So some fixed, and well, actually, let's use finite, it's a better term, a finite number L. It's a very, like, if you think about it, it's a very weird concept. This is an infinite sum. This is a sum that never ends. But at the end of the day, the sum is equal to 5 or 3 or 1/2 or -2. But in fact, it is. Mathematically, we can prove that it is. So we don't need to know much about series in terms of generalities. We need to know a little bit more about details about some types of series. That's what we're going to do. We're going to begin with the first big type of series, which is geometric series. So what is a geometric series? A geometric series, ladies and gentlemen, is when you have the summation from n equals to, it doesn't really matter where n starts, but the definition of a geometric series in textbook, they do n equals 1 to infinity of a times r to the n minus 1. And r is what we call the ratio. I'll tell you what this is. So this is sort of the textbook definition. What does it mean? It means that the terms of the series, every one of these terms, so you get a term an by multiplying the term before it by a constant ratio. Look, if you write down these terms, when n is equal to 1, you get a. When n is equal to 2, you get a times r. When n is equal to 3, you get a r to the 2 plus a r to the 3 plus until the end of line. So you notice that from this term to this term, you're multiplying by r. From this term to this term, you're multiplying by r. So a geometric series is when the next term is begotten, you get the next term by multiplying the previous term by r. Really what you should remember from all of this, and this is very important, whenever we talk about a geometric series, it means we're talking about an exponential function. Right? It won't always have this form. This form is kind of like the tuxedo form, like the form it wears to parties. So it could be really, really anything. Let me show you some examples of geometric series that don't match this form. So for example, I can take the summation from n equals 0 to infinity. There's no problem in starting at 0 with 1 over 2 to the n. Clearly, this doesn't match the form that we have on top. And yet, if n is equal to 0, that's 1. If n is equal to 1, that's 1/2. If n is equal to 2, that's 1 over 2 squared, which is 1/4. Then 1 over 2 cubed, that's 1/8, plus dot, dot, dot. We can clearly see that going from one term to the other, the ratio is 1/2. You multiply by half to get from one term to the other. If you wanted to write this as an exponential, like just to change its form to make it match this or make it an like a pure exponential function, you can say that this is 1/2 to the power n. Because technically 1 is like 1 to the power n. So 1 to the power n over 2 to the power n, you just write it as 1/2 to the n. And you see the ratio appears on the inside. So anytime you raise something to the power n, that's going to be your ratio. And if you write down the terms again, you get back these terms. Okay, let me show you another example of a geometric series that doesn't look like just this special form. So let's say you have, I don't know, the summation from n equals 1 to infinity of 2 to the 3n over 3 to the 2n. Right? So How do I know that this is a geometric series? Well, one way to do it is to write down the terms. So if n is equal to 1, we're going to get 8 over 9, or 2 to the 3 divided by 3 to the 2, if you don't want to compute it. When n is equal to 2, that's 2 to the power 6 over 3 to the power 4. When n is equal to 3, it's 2 to the power 9 over 3 to the power 6, and so on. So you can see that going from one term to the other, the ratio is 2 to the power 3 over 3 to the power 2. You multiply by 2 to the power 3 to get this, and by 3 to the power 2 to get this. Okay, how can we rewrite our series in a way that makes the r appears very, very clearly? You can write this as this is the summation, n equals 1 to infinity. 2 to the 3 to the n, that's 2 to the 3 all to the n. 3 to the 2n, that's 3 to the 2 all to the n. So then I can write this as summation n equals 1 to infinity. 2 to the 3 is 8. 3 to the 2 is 9. And they're both to the power n. And you can see that this is your ratio. Right? Okay, why do we care so much about the ratio of geometric series? Why is it so important? Because of a very important theorem. A geometric series, when you have a geometric series, it's convergent if the ratio is strictly between -1 and 1. And if it's not, we could say equivalency here. So if the ratio is between -1 and 1, the series is convergent. And if the series is convergent, again, a geometric series, the ratio must be between -1 and 1. Now, if it converges, it converges to, and this is a very rare fact, knowing what the series converges to. Please look at this. I think you memorize it as a over 1 minus r. I prefer if you memorize this as first term over 1 minus r. First term over 1 minus the ratio. Why do I prefer this over the formula of a over 1 minus r? Because a, it's not always the first term. A is the first term only if you have it in this special form, right? If you have it in this special form, then the first term is A. But if you have it in a different form, then A is not, like sometimes A is not clear what it is, and sometimes like it's even if you see an A, sometimes it's very tricky. It's not the actual A that you think it is. For example, look at this series. Okay, so let's just look at this series. Is this convergent or divergent? Well, this series, the ratio, we just found it upstairs, is 8 over 9. It is between -1 and 1, so this is convergent. So what does it converge to? So what is this equal to? Right, what's A in here? There's no A. Right, what are you going to use as A, right? So it's better if you use the first term. And the first term is 8 over 9 over 1 minus the ratio, which is 8 over 9. So it's 8 over 9 divided by 1 over 9, and the answer is 8. So this series, it converges to 8. Let me give you another very quick example to discuss conversion. So let's say I have the summation from n equals 2 to infinity of 2 to the 4 minus 2n, or 3 minus 2n, let's say. Is this convergent or divergent? And if it's convergent, what does it converge to? So one way to do this is to write down the terms, or if you don't want to write down the terms, let's change this right away to make it look like to make the ratio pop out, like to see what the ratio is. This is the same thing as the summation of 2 to the 3 times 2 to the minus 2n, right? Because when you multiply terms that have the same base, you add the exponent. Remember, if you have a to the m times a to the n, then this is a to the m plus n. So we then write this as the summation from n equals 2 to infinity. This is 8 divided by 2, or let's just say 8 times, sure, let's divide it. 8 times 2 to the 2n. So we can write this as the summation from n equals 2 to infinity of 8 divided by 4 to the n, right? Because 2 to the power 2 is 4. Or if you want to write it in a different way, you can say this is summation n equals 2 to infinity 8 times 1 over 4 to the n, which makes the r becomes apparent. Right? We know the r when it's n. This must be n. If you want to read r right away, it must be n. So it can't be 2n, let's say. So here it was 2n. So I cannot say the ratio is 2. If you want to read the ratio, the power has to be n. So the ratio is equal to 1/4. So the series is convergent. So what is it equal to? So the summation from n equals 2 to infinity of 2 to the 3 minus 2n is equal to, excuse me, first term over 1 minus the ratio. So first term, when I put n is equal to 2, remember first term is when n is equal to 2. So you replace n is equal to 2 here. You're going to get 2 to the minus 1 over 1 minus the ratio 1/4. So this is a half over 3/4. So it's 2/3. Right? Great. You haven't asked me any questions so far, so I assume everything is clear. Now we want to talk about a very, very special series. So now we have a very special series that 100% will show up on your final. There is no final. You can go back as far as you want in the finals of 172. There's no final of 172 that doesn't have this series on. What is this fantastic series? It's the summation from n equals 0 to infinity of x to the power n. So this is 1 plus x squared plus x cubed, and so on. Okay, what is so special about this series? Well, I'll tell you. This is a geometric series, and the ratio is x. So if, big if, minus 1 is less than x is less than 1, so if x is between minus 1 and 1, then this series is convergent, and the summation from 0 to infinity of x to the n is first term over 1 minus the ratio. I cannot tell you how useful this is. This is incredibly useful. Right? So this is very, very useful. So this is called the power series of 1 over 1 minus x. So this is called, so this is called a power series. I'm going to say more about power series later. Just think about power series. Power series, it's a series with a variable. It's a series with a variable. I will say more on it, much more on it later. Is R always the n equals to 1 term? No. R is what you multiply by to get the next term. So R is whatever you raise to the power n. Right, Johnny? I don't know what you mean n equals the first. There's a typo there, but if you fix it, I can answer you. So R is what you have here raised to the power n, and it must be to the power n, not 2n, not 3n, not 1 minus 5n. Yes, exactly. So what you multiply by r to get from here to here. You multiply by r to get from here to here. One way to get r, by the way, is not thinking of it as a multiplication. Take this term divided by this term, you get r. Take this term divided by this term, you get r. Take this term divided by this term, you get r. That's what makes it a geometric series. It has a common ratio. So getting from one term to the other is done using the same ratio every single time. Is it clear? Right. So what I want from you, and this is very, very important, please let me know if you're not okay with my explanation, and I'll review it. What I want from you is not to memorize it like this. No, I want you to memorize it in a much more general form. I want us to know that when we have 1 over 1 minus box, so I want to use x, I want to use box, is equal to the summation from n equals 0 to infinity of box to the power n, as long as box is between minus 1 and 1. That's what I want you to remember. And it's basically exactly what I just said. So this is a geometric series, right? So this is a geometric series. The ratio is box. So if the box is between minus 1 and 1, the series is equal to first term over 1 minus the ratio. And the first term is when you take box to the 0, which is 1, right? So it's exactly what I just said here. It's exactly what I said here. But instead of x, I want you to think of it as box. So 1 over 1 minus box. Why? Because this is a very, very popular question on finance. So for example, they will ask you for a power series representation of some function. Let's say the function here is 1 over 1 minus 5x. And then they will ask you for the interval of convergence. I'll tell you what this means. So the interval of convergence, this is what? These are the value or values of x for which the series converges. Now, in a different course, in a different settings, this would be a whole lot of work. In this course, for us in APSC 172, it's really just means this. So this series is equal to this only if the ratio is between minus 1 and 1. So let's look at this. How do I write the power series representation of this? So how do I write this as a series? And like 99% of the cases, we're going to be using this. Maybe not 99, maybe like 90%, because the other 10% are the other special Maclaurin series, e to the x, sine x, and cos x. But this is heavily used on that. So here, I have 1 over 1 minus 5x. So 5x is the box, right? So I'm going to write this as the summation from n equals 0 to infinity of 5x to the power n, which we can write as the summation n equals 0 to infinity of 5 to the n, x to the n. And when can we do this? What's our interval of convergence? When are we allowed to write this series equals to this function? We are allowed to do this when our box is between minus 1 and 1. Therefore, when x is between minus 1 over 5 and 1 over 5. Right? So that, ladies and gentlemen, is a very, very popular question. Although this is a very simple function, they can ask us like a large variation of this. So let's practice some variations of this. So let's say they would ask you for a power series, like from now on, PS will just mean power series. So let's say we want a power series representation of, and let's say that you have 5x over 3 plus 2x squared. And you know what? Let's find an interval of conversion source. So where is this series conversion? How do you write the power series of this? Remember, our goal will always be to come back to this. This is our benchmark. This is our baseline. We always want to come back to 1 over 1 minus x. So let's go back to this. I'm going to put 5x on the side. And I'm going to say this is 1 over 3 plus 2x squared. Right now I need a 1 here. So I'm going to factor out the 3. And that will be 1 plus 2x squared over 3. I'm getting closer to the form I like. Now, this plus, I'm going to change it to 5x over 3, 1 over 1 minus, and then here minus 2x squared over 3. And that, ladies and gentlemen, is your box. So this is equal to 5x over 3, the summation from n equals 0 to infinity of minus 2x squared over 3 to the power n. I'm going to pause for a second. Do you have a question about what I just did? Of course, how can we make this jump? We need to have box between minus 1 and 1, but I'm going to write that in just a second. Let me tidy up a little. So this is 5x over 3. This is the summation from n equals 0 to infinity. There's a minus, so minus 1 to the n, 2 to the n, x to the 2n over 3 to the n. Summation n equals 0 to infinity. I'm multiplying the 5n, so there's a minus 1 to the n times 5. Now x times x to the 2n, that's x to the 2n plus 1. Remember, when we multiply expressions having the same base, we add the exponents. And 3 times 3 to the n, that's 3 to the n plus 1. Now, when can I do this? I can do this when minus 2x squared over 3 is between minus 1 and 1. And here is a part that usually confuses the students, so please pay attention. So if minus 2x squared over 3 is between minus 1 and 1, if I multiply everything by a minus, I'm gonna change the signs of the inequality. So 1 is bigger than 2x squared over 3 is bigger than minus 1. But I don't like to read it that way. That way is very confusing. So I'm going to read it backwards, which means minus 1 is less than 2x squared over 3 less than 1. Now, it seems like it hasn't changed from here to here, but it has. We just moved it around, but then read it in the proper order. So that means minus, technically, that can't be negative, right? Technically, that can't be negative. So 0 is less than 2x squared over 3 less than 1. So that means 0 is less than x squared is less than 3 over 2. That means x is between minus the root of 3 over 2 and plus the root of 3 over 2. Right, if x squared is less than 3 over 2, then x is between minus the root and plus the root. And that, ladies and gentlemen, is what we call the interval of convergence. Questions? I'm gonna make this a little bit harder now. So let's see. How about we want to do this a little bit harder? This is a very, very popular one. How would you do, sorry. So, how do we make this a little bit harder? Find the power series representation of ln 1 plus x. And let's always add the interval of conversion. Well, as a first look at this, it really has nothing to do with 1 over 1 minus x, right? Remember, our benchmark is what we have 1 over 1 minus box is equal to the summation n equals 0 to infinity of box to the power n, as long as box is between minus 1 and 1. Okay, then at first look at this, what does this have to do with this? But then it does. How can I link these two? Here's how I can link these two. Let's call this y. If we take y prime, if I derive ln of 1 plus x, I get 1 over 1 plus x. And that's pretty much this with a negative sign. So this is 1 over 1 minus x, and that I can write as a series summation n equals 0 to infinity of minus x to the power n, which is the summation from n equals 0 to infinity of minus 1 to the n x to the n. Right, but I don't want y prime. I want y. I want ln of 1 plus x, which is the integral of this. So let's integrate, no problem. Y is equal to, when you integrate this, you only integrate the x's, right? The constants just stay. So minus 1 to the n is a constant. What's the integral of x to the n? It's x to the n plus 1 all over n plus 1. Technically plus c, but c is going to be for us always, whatever the function is at 0. The function at the center of convergence, it's called, which in all of these cases is 0. So what is f of 0? It's going to be ln of 1 plus 0, which is ln of 1, which is 0. So c is 0. Therefore, we just showed that ln of 1 plus x is equal to the summation n equals 0 to infinity minus 1 to the n x to the n plus 1 all over n plus 1. Now, when can we do this? Remember the interval of convergence. We can make the jump from here to here, right? We can make the jump from here to here if minus x is between minus 1 and 1. Now we saw that this can just be written as x between minus 1 and 1. So the interval of convergence is x being between minus 1 and 1. Did you guys get what I just did? Okay, I'm going to ask you another one, and this is a very, very popular one. Queens love arctangent. How would you find a power series representation of y equals arctan x? Again, this is our benchmark. This is what we're hoping to use. And somehow we need to link arctangent to this. Now, ln of 1 plus x gives you the whole hint you need. So can I give you 30 seconds? How would you find the power series representation of arctangent x? And of course, let's always add the interval of convergence. Okay, 30 seconds, give that a shot. So, right, so it's not a secret. We're gonna derive y prime is equal to 1 over 1 plus x squared, which we can write as the summation from n equals 0 to infinity of minus x squared to the n, which is the summation from n equals 0 to infinity of minus 1 to the n x to the 2n. Now, we don't want y prime. We technically want y, so we want y, which is arctangent of x. So we're going to integrate. The integral of this is the summation 0 to infinity minus 1 to the n x to the 2n plus 1 over 2n plus 1. Don't forget plus c. But what is c? We said that c would always be f at 0, which is arctangent of 0, which is 0. Now, in most of the cases, c is 0. But there are cases where c isn't 0, and that's not weird at all. Like, this shouldn't freak you out if c isn't 0. Just say whatever c is. Right? Okay, I'm going to ask you some slightly harder ones now. Okay, I'm very, very happy. This is, I did this last term. I was teaching this winter not last year, and this showed up on the 2022 final. I had done it in the session. So if you look at the 2022 final, they asked them exactly this, and I had done this in the session. So they gave them the arctangent, by the way. I'll do this next part. It's fun. But I mean, they asked them this. This is what so they asked them to write this as a series. No, they only asked for a Taylor. Oh, cute. Anyway, I'm gonna ask you this. So let's take, I want a power series representation of 1 over 1 minus x squared, or 1 plus 1, whatever. It doesn't matter if it's 1 minus or 1 plus. 1 minus might be a little bit easier on you. So what is the power series of 1 over 1 minus x squared? Then after this, there's going to be some like even more complicated power series. Again, our benchmark is the 1 over 1 minus x. This is what we're hoping to compare to. Now, we really shouldn't multiply series. Like, you shouldn't say 1 over 1 minus x times 1 over 1 minus x. That's a terrible idea. Multiplying series is just a terrible, terrible idea. So the link we want to create is either by a derivative or an integral. Now, if you derive this, it gets nowhere close to this. But then you realize that if you take the derivative of 1 over 1 minus x, you get 1 over 1 minus x all squared. There's no minus because then you multiply by the chain rule, by the derivative of 1 minus x. So really, that function that you want is the derivative of that function that is your benchmark. So the 1 over 1 minus x all squared, that's equal to the derivative of the summation n equals 0 to infinity of x to the n. Now, please pay attention here. When we derive, we lose a term. So we start now at n equals 1 to infinity of nx to the n minus 1. You say, why do we lose a term? Because the summation of x to the n, that's 1 plus x squared plus x cubed dot. And when you derive 1, you get 0. So the term n is equal to 0, which is 1, its derivative is 0 and it's gone. So you start your series at n is equal to 1. Remember this, when you derive, you lose a term. And we are able to make the jump from here, like we're able to do the jump from here to here as long as minus 1 is less than x is less than 1. Okay, I'm going to do harder questions. But first, let's see. Let's look at 2021. Just to show you that we're doing exactly what they ask. Here we go. Find the Maclaurin series of arctan x over x. Now, Maclaurin series is an example of a power series. I will explain what Maclaurin series and Taylor series are in just a second. So just think of this Maclaurin right now, Maclaurin series, think of it as just power series. So find me the power series of arctan x over x. Okay, see, here's, please pay attention to what I'm going to say here. Step number 1 would always be to find the power series of arctan x, which we did already. And step 2 is you just adjust. Adjust means you just change it to fit whatever they're asking you. So we did arctangent of x. It's right here. Now, in some instances, they will give you this. In some instances, they will give you this. So in step 1, it's here. So this one, so you don't see which is done above. So we just did this, the arctangent of x. So what you want to do is now you want to adjust this to meet this. Now here it's very simple. It's just arctan x over x. They're being very nice that year. So if arctan of x is that series, so 1 over x arctan x is 1 over x times this sum. And when you divide x to the 2n plus 1 divided by x, so when you divide, you minus the exponent. So that would be the summation n equals 0 to infinity minus 1 to the n, x to the 2n over 2n plus 1. Right? When we divide, a to the m divided by a to the n is a to the m minus n. Now, of course, this could have been 100 times, like not 100 times, but like more difficult than what they asked in 2021. They could ask you to find the power series of arctangent root x all divided by x cubed. Like, see here, they just kept it as arctan x, but it could have been arctangent of anything. right? So step one, as always, would be to find the power series of arctan x. So you find it like we did on top and you get this. So first step is to get this. Then the second step is you adjust to meet whatever they're asking you to find. So arctangent of root x, which is x to the half, is equal to the summation from n equals 0 to infinity of -1 to the n, x to the half, all to the power 2n plus 1 over 2n plus 1, which is the summation from n equals 0 to infinity, -1 to the n, x to the half times n, 2n is n plus a half over 2n plus 1. Now we're dividing this by x cubed, so 1 over x cubed arctan x to the half is 1 over x cubed times what we just found here. So we minus the exponent of x, summation n equals 0 to infinity, -1 to the n, x, n plus a half minus 3, so n minus 5 halves divided by 2n plus 1. Do you follow what I'm trying to say? Sometimes it's even a bit more work than this. So sometimes they'll ask you to find, let's say, the integral from 0 to 0.2 of, let's say, ln of 2 plus x squared over x cubed dx. And sometimes they ask you to find the, let's say, this as a series. Can I give you 30 seconds to tell me what do you do in this case? So what would you do in this case? What would be your step one? The last step, Cecilia, you mean this? Like going from here to here? Well, look, you have x3 and you have x to the n plus a half. So technically you have x to the n plus a half divided by x3. So it's as if you have x to n plus a half minus 3, and a half minus 3 is minus 5 halves. Is that clear? Right, a half minus 3 is 5 halves, is minus 5 amps, and you get this. So you're minusing. Yes, thank you for asking, Cecilia. Please do like Cecilia did and ask if there's anything you don't understand. Okay, so what is the first step in this one? So the first step in this one is to find the power series of ln 1 plus x. Then adjust it to find all of this. Now, we did this earlier. We found that the summation of ln 1 plus x is the summation of -1 to the n, x to the n plus 1 over n plus 1. This one was done earlier. So step number 2 is I need to adjust it to find whatever they want from me. So first step is how do I adjust the ln 2 plus x squared. See, that 2 is very annoying. And if this is the first time you see this, then please pay attention. So I take ln, and I factor the 2. That gives me 1 plus x squared over 2. And this is one of the most difficult ones that you'll see. So let's put a spice next to this. So this is one of the most difficult ones that you usually see. So now you have ln of this times this, and we know what when you ln of a product, so it's ln of 2 plus ln of 1 plus x squared over 2. So when you have ln of a times b, then this just becomes ln of a plus ln of b. That's the rule that I used right here. And now, see this, ln of 1 plus x squared, ln 1 plus x. Now I could use this. So I replace x by x squared over 2. So this is ln 2, which is just going to stay there. You know what? Maybe it wasn't such a good idea. Okay, let's just put a ln 2 here. Let's not divide by x3 because it won't be a power series. Let's just leave it as this. I'll do one with divided by x3 in just a second. So this is ln of 2 plus this is going to be the summation n equals 0 to infinity. We're going to do minus 1 to the n, x to the 2 over 2 to the n plus 1, all divided by n plus 1. And this would be ln of 2 plus the summation from n equals 0 to infinity, minus 1 to the n, x to the 2n plus 2, all divided by 2 to the power n plus 1 times n plus 1. Now, the integral from 0 to 0.2 of ln of 2 plus x squared, that's the integral from 0 to 0.2 of ln of 2. Great, that's not a difficult integral. Then from 0 to 0.2 of this sum. And remember, when we integrate or when we derive, we only integrate or derive the x term. So the integral from 0 to 0.2, well, here it's just x times ln 2 from 0 to 0.2 plus here it's the summation from n equals 0 to infinity. There's minus 1 to the n all over 2 to the n plus 1 times n plus 1. Now we're going to take the integral of x to the 2n plus 2, which is x to the 2n plus 3 over 2n plus 3 from 0 to 0.2. And final answer is 0.2 ln 2, which is just there. And then when we plug in x is equal to 0.2, that would be minus 1 to the n, 0.2 to the 2n plus 3, all over 2 to the n plus 1, n plus 1, 2n plus 3. And when you plug in 0 and 0. And usually after this step, I'll see it here, usually after this step, you are asked for an error estimation, which we will definitely do. There's two types of error estimations. There is either the alternating series error estimation or the Taylor polynomial error estimation. So usually after this step comes right away, estimate this with a certain error. But we're not there yet. But I just wanted to show you how, how the series of questions come in. So they'd ask you this, you find it, and then you go and you find an error estimation. This seems a lot. One bit of advice to you: if you're copying all of this after me, the session will be very, very exhausting. So I do not recommend you copy all of this after me. You're going to be exhausted and you're not going to be paying attention. Again, you could do whatever you want. I respect your choices, but I totally do not recommend that people write after me for the entire session. You get tired and your goal would be to copy, not to understand. But the video is going to be available and the notes are going to be available. So you can just copy all you want later. All right, so I'm gonna come back to this, but before I come back to this, I want to take a short sort of window here to talk to you about what is a Taylor series, what is a Maclaurin series, and what's a Taylor polynomial. Can I go over the second step? You mean this step from here to here, or you mean the entire second step? Here to here? The one after that. So going from here to here? No problem, Saad. You see that ln of 1 plus x is equal to this, right? So this we did earlier, and we showed that ln 1 plus x is equal to this series. Now I'm doing ln 1 plus x squared over 2. So how about I replace the x by x squared over 2? So instead of x, I'm replacing that by x squared over 2. You see what I just did? So I thought of this as not ln 1 plus x, right? I think of this as ln 1 plus box, and I put x squared over 2 in that box. That's going to be our strategy all the time. We're going to find the series with an x. We're going to pretend the x is a box, and then we're going to replace what we need inside that box. Any other questions, guys? So, if not, I want to talk to you about what a Taylor series. It is a theorem that any function f of x can be written as a power series. And again, a power series is a series that has an x in it. So any function f of x can be written as the summation from n equals 0 to infinity of the nth derivative at some point a over n factorial x minus a to the power n. So this is the Taylor series. We say about x equals to a. So this is the series about x equals to a, or some people say in powers of x minus a, or centered at a. Some people use the terminology centered at x equals to a, or centered at a. That means just the a is here. That means it's all x minus a to the power n. So, by the way, if you want to expand this, and you should know how to expand this because we need it in Taylor polynomials, the first term is when n is equal to 0. So it's basically f of a. 0 factorial is 1, and x minus a to the 0 is 1. Then we have f prime at a divided by 1 factorial, which is 1, times x minus a. Then f double prime at a over 2 factorial x minus a to the 2. Then f triple prime at a over 3 factorial x minus a to the power 3, and so on and so forth until the end of time. Now, I want to say something very, very, very important. In a Taylor series, as in a Maclaurin series, as in any power series, what would be the coefficient of x minus a to the power n. The coefficient of x minus a to the power n. So what's the coefficient of x minus a to the power n? Is always the nth derivative at a divided by n factorial. This is very important to remember. The coefficient of x minus a to the power n is the nth derivative at a divided by n factorial. That's a very, very important quantity to remember. Now, what do we call a Maclaurin series? Maclaurin is basically Taylor, but a is equal to 0. Maclaurin is simply when a is 0, when the center of convergence is 0. It's just exactly Taylor. So you write f of x is equal to the summation from n equals 0 to infinity, the nth derivative at 0 over n factorial, x minus 0, so x to the power n. And if you were to expand it, this is f of 0 plus f prime of 0 x plus f double prime at 0 over 2 factorial x squared and dot dot dot. Again, what's the coefficient of x to the n? It's fn. I mean, we don't need to rewrite it, but let's just use it as a note. So if we have a Maclaurin series, the coefficient of x to the n is the nth derivative at 0 divided by n factorial. Very, very important. And it's a question that comes up on tests. Okay, so now the next definition is, what is the Taylor, not series, but what is the Taylor polynomial of degree n? Well, you guys, it's just the Taylor series, but then you stop at power n. So it's of degree n, which means you stop at power n. So you call this Tn of x, or some people call it Pn of x. I think you use T. So Tn of x is the summation of I equals 0 to n of the ith derivative at a divided by I factorial x minus a to the power I. Basically just stop at n, right? So look here, n. You stop at power n. And that is also a popular question. There's something that I'm going to do later. I'm not going to talk about it right now. I'll do later. So later we will talk about the error term, the Taylor error term. That's probably one of the last things we talk about today, which is the energy. But later. For now, I want to stick to Taylor, Maclaurin, power series, this kind of stuff. Okay, so when they tell us find the Maclaurin series, basically they're asking us for a power series. When they tell us for a Taylor series, they're asking us to find a power series. So power series is sort of the general umbrella. All of those are power series, and then Taylor and Maclaurin are particular of power series. Now, in terms of Maclaurin series, there are a couple of famous Maclaurin series. This is the part that I always ask you about. I don't know which ones are you allowed to use as in to memorize. So what are the ones that you're usually allowed to memorize? The standard ones, the standard one that's the basic minimum is you are allowed to use 1 over 1 minus x as the summation of x to the n, as long as x is between minus 1 and 1. You are allowed to use sine x as the summation 0 to infinity. And sometimes they give you those, right? Sometimes they just simply give you those. I don't know, every year is different, so I always ask. So this is sine x, and here x can be anywhere it wants. There is cosine x, and here x can be anywhere it wants. And there is e to the x, which is the summation 0 to infinity x to the n over n factorial, and here x can be anywhere it wants. Now, are you allowed to memorize the series of arctan x? I don't know. Are you allowed to memorize the series of ln 1 plus x? I don't know. But even if you're not allowed to memorize them, I showed you how to find them, right? Arctan x is the summation from n equals 0 to infinity of minus 1 to the n x to the 2n plus 1 over 2n plus 1. And ln of 1 plus x is the summation n equals 0 to infinity of minus 1 to the n x to the n plus 1 over n plus 1. Now, this means, it means, are you allowed to memorize them? It doesn't mean that if this is true or not. So are you allowed to memorize those? I don't know. But I showed you how to find them, right? So I showed you how to find them. So if you're not allowed to use them as is, you can actually just find them the way I showed you how to find them. Right? All right. So let's get more questions. So in 2020, here's what they asked them. They gave them f of x is equal to the integral from 0 to x of e to the t squared dt. And then they asked them in part A to find the Maclaurin series. In part B, they asked them to find T9 of x, so the Taylor polynomial of degree 9. And I'm adding, so this is extra. No, this is not extra. This is what they asked. What is the 17th derivative at 0 of x? So what is the 17th derivative at 0 of this f of x? Right, and this is a very, very popular question. Right, so this is a very popular question to be asked these things in this order. I'll tell you what also is another popular question in a second. And you don't have to take my word for it, right? They gave you, I think, 2020, 2021, and 2022. And I gave you a bunch of older finals. I can't remember the ones I gave you, but on the course page, actually, I can tell you which ones I gave you. On the course page, I gave you, nope, that's the midterm. I don't know where they are. Just give me a second. I'll tell you which ones I gave you. On the course page, yeah, here they are. Supplement. It'll just take a second to load. Open Sesame. I gave you from 2014. Wow, I did all that. I forgot. I gave you from 2014 to 2019. They gave you from 2020 till 2022. So you have like 8 years worth of finals. All of them are just solved. All of them are in detail. So that's a lot of finals for you to work with. It's a lot of good practice. And then again, don't take my word for it, but look at the finals. You realize that even though they're not identical, they always follow the same pattern, and there's always questions that come up very, very often. So you're not in shortage of practice problems. Excellent. So let's see. How do we write the power series of this for part A? Remember, we start with e to the x. So e to the x is the summation from n is equal 0 to infinity of x to the n over n factorial. So what's e to the t squared? I replace x by t squared. This is the summation n equals 0 to infinity of t squared to the n over n factorial. So this is the summation n equals 0 to infinity t to the 2n over n factorial. Now I don't want e to the t squared. I want the integral of e to the t squared. So f of x is equal to the integral from 0 to x of the integral of this of this sum dt. Remember, we only integrate the terms with t. So there is 1 over n factorial is just a constant, it stays there. So this is to the t to the 2n plus 1 over 2n plus 1 from 0 to x. So when I replace t by x and then t by 0, this is x to the 2n plus 1 all divided by n factorial times 2n plus 1. And that is the Maclaurin series of f of x. Okay, what is T9 of x? So this is the Taylor polynomial. This is the Taylor polynomial of degree 9. So we're going to stop at degree 9. Well, we have it right here. So for n is equal to 0, we're going to get x. For n is equal to 1, we're going to get x3 over 3. For n is equal to 2, that's x to the 5 over 2 times n is equal to 5. Then x and n is equal to 3. 3 times 7, and also 3's factorial is 6. And then x to the 9 divided by n is equal to 4. That's 4 factorial, which is 24 times 1. And the last part here is, what is the 17th derivative at 0 of f? Please, please, please pay attention. This is new. So, any questions about this before I move on? By the way, you're really, really silent. So I'm assuming everything is fine. I'm assuming you're following. There's nothing unclear. I'm assuming if you had any question, you would ask me, right? We have this unspoken rule of if anything is unclear, you will tell me. Okay, so what is the 17th derivative? Remember something very important, I said it before. The coefficient of x to the 17 is the derivative, the 17th derivative at 0 over 17 factorial. Okay, but what is the coefficient of x to the 17? Like here, what's the coefficient of x to the 17? Right, if you were to continue f of x, you start with x plus dot dot dot. What would be the coefficient of x to the 17? Right, so what would give you the coefficient of x equals to 17 here? That would be the term where n is equal to get 17, n is equal to 8. So what would be the coefficient when n is equal to 8? That would be 1 over, so x to the 17, 1 over 8 factorial times 17. Do you understand the first bit? So the coefficient of x to the 17 theoretically is the 17th derivative at 0 divided by 17. Now we look at our series, right? We look at our series. So what is the coefficient of x to the 17 in my series? So if I continue with this, right? If I were to continue with this, when I hit 17, x to the 17, that's when n is equal to 8. I'm going to get 8 factorial times 17. So that means what? That means 1 over 8 factorial times 17 is supposed to be the 17th derivative at 0 divided by 17 factorial. And therefore, you can now get the 17th derivative. So f order 17 at 0 is 17 factorial over 8 factorial times 17. And you simplify this however way you want. Okay, let me ask you this other question. So, let me see. Okay, so first part is find the Maclaurin series of x squared ln of 1 plus x squared. So this is part A. And part B, just give me a second. Part B, we want the 24th derivative. So let's call this g of x. It's easier. So the derivative g of x is equal to. So what is the 24th derivative at 0? And part C, what is the 19th derivative at 0? And of course, I will remind you, I'll give you a reminder here that ln of 1 plus x is the summation from n equals 0 to infinity of minus 1 to the n, x to the n plus 1 all over n plus 1. Right? It is time for our break, so this is perfect. I'm going to leave this problem on, so if you guys want to practice it on the break, that's fantastic. If you don't want to practice it on the break, then after the break, I'll come back and I'll solve it. Right now it is 6:50. Let's take our first break to be only 15 minutes, and then the next break will make it 25 minutes. Instead of taking it 20-20, I think we'll be a lot more tired later, so we might need a bigger break later. So let's take the first break 15 minutes. And then if we need a bigger break later, then great, we take it. If we don't need it later, then we would save 5 minutes of break. And those are 5 extra minutes of session time. So 15 minutes, ladies and gentlemen. Let us be back after 15 minutes to continue on this problem, and then other alternate. After this, I'm going to do alternating series, and then error terms, and then we'll just continue to cover everything. Please, 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 if you have any questions or comments, let me know. See you in a bit. Hey everyone, we're back. So let's see. How do we find the Maclaurin series of this g of x? Well, you start by finding the Maclaurin series of ln of 1 plus x squared. And you know that ln 1 plus x is equal to this. So you replace x by x squared. That's going to give you minus 1 to the n, x squared to the n plus 1, all divided by n plus 1. And this is the summation n equals 0 to infinity minus 1 to the n, x to the 2n plus 2 all over n plus 1. And then you want to multiply it by x squared. So x squared times ln 1 plus x squared is equal to x squared times the sum that you found for ln of 1 plus x squared. And this would be the summation from n equals 0 to infinity. Remember, we're taking x squared and we're multiplying it by x to the 2n plus 2. So we add the exponents. So x to the 2n plus 4 all over n plus 1. And that, ladies and gentlemen, is our Maclaurin series, no problem. Fantastic. Now let's talk about what is the 24th derivative at 0. Great. So the 24th derivative, remember the trick for this, the coefficient of x to the 24 is the 24th derivative at 0, all divided by 24 factorial. Great. So we ask ourselves in here, what is the coefficient of x to the 24th? So when we write g of x is equal to, it's going to be a bunch of terms. What's going to be the coefficient of x to the 24? Right. So to get 24, we need n to be 20. Right. So to get to 24, if we make that's n is equal to 20. So the term n is equal to, not 20, 10, I mean, sorry. For n is equal to 10, when you make n is equal to 10, you get x to the 24. So that would be minus 1 to the 10, all divided by 11. Right? Minus 1 to the 10 divided by 11. That's what happens when you take n is equal to 10 times x to the 24. And therefore, g to the 24 at 0 divided by 24 factorial is that minus 1 to the 10, which is just 1 over 11. And therefore, if you want the 24th derivative at 0, that's 24 factorial over 11. That's a very popular question. I have seen it asked a few times. Fabulous. Let's go to part 3. So what is the 19th derivative at 0? Well, it should be the exact same thing, right? So we remember that the coefficient of x to the 19 is g to the 19 at 0 divided by 19 factorial. Great. Now go to the function that's g of x. This is g of x. What's the actual coefficient of of x to the 19? Anybody cares to tell me? Well, we had g of x is equal to this. So how would I get to x to the 19? In reality, there is no x to the 19 term. Again, no, that's what it means is that in g of x, you're just going to add a bunch of terms, and then you're going to get 0x to the 19 plus whatever. If there is no x to the 19 term, that means the coefficient of x to the 19 is 0. That's how you get no x to the 19 term. It means the coefficient of x to the 19 is 0, which tells you that g to the 19 at 0 over 19 factorial is 0. Well, that basically means the 19th derivative at 0 is 0, because there is no x to the 19 term. Do we get this? Any questions about this? Any comments? You are very, very silent today. Maybe it's Sunday and you're just chilling. Well, Cecilia, what would you make n to get x to the 19? So what should n be so that you get x to the 19? That's an excellent question. Right? You want 2n plus 4 to be 19. So that means you want 2n to be 15. So you want n to be 7.5. Can you make n equal to 7.5? So this is not possible. Therefore, there is no x to the 19. Do you see that? Thank you for asking, Cecilia. When you ask a question, you make the session better. So you ask, I will answer, and the session becomes better. When you ask a question, a lot of good things happen, because some people may think, okay, wow, Antoine is going fast. Well, Antoine will go fast. I will go fast if there is no questions. If, I mean, nobody's saying anything, nobody's asking me anything. So I assume that you understand. And naturally, a prep session is fast because I'm explaining what you've done in a bunch of weeks in 4 hours. So I naturally have to go fast, but I will stop. I will say things again. I will re-explain. So if you want to slow me down, maybe ask a question. That way I answer your question and you understand, and it doesn't seem like I'm going fast anymore. All right, so now we understand what a power series is. We understand those famous Maclaurin series. I want to talk to you about, and this is a very, very popular question, about writing a Taylor polynomial, or we could leave that till a bit later, when we write the Taylor polynomial error bound. So we could do that later. Let's now talk about alternating series. So let our next topic be alternating series, and this is again a very popular question on tests. Please don't take my word for it, check the tests. I've given you from 2014 till 2019, and they gave you 2020 till 2022. So you have plenty of finals to check. And you'll see that there is no final without a question on alternating series. Okay, so what is an alternating series? Simply put, it's a series where we alternate terms. So it's the summation from n equals 1 or 0, doesn't really matter, just pick one, or 7 if you want, like start anywhere you want, right? Of -1 to the n dn. So this is an alternating term. So this is what makes it alternating, because it's plus minus plus minus. Also, please remember, this is an important note to keep in mind, that cosine n pi, if you see cosine n pi, that's the same thing as -1 to the n. Great. So this is b0 when n is equal to 0, then minus b1 when n is equal to 2, plus b2 when n is equal to 3, minus b3, plus dot dot. Right, so when does an alternating series converges? I haven't seen them ask you many questions about this, so I haven't seen them ask you a lot of, any questions, to be fair, about the convergence of an alternating series. So I'm writing this as a note, as a separate note. You will tell me if you've done anything about this. So when is an alternating series convergence? So an alternating series converges, you need to check two things. For it to converge, you need to check two things. If the limit of the term Bn is 0 and Bn is decreasing. So if it's a decreasing term, and it goes to 0. Again, I haven't seen them ask you any questions involving show that this series converges. They've basically asked you questions about estimation of alternating series, which is what I'm going to do right now, the error term. And I guarantee you there's going to be something on the error. Like if there's no error term on the final, it would be a very strange final. So we assume that the summation from n equals 0 to infinity of -1 n bn converges. So of course, there is no error if the series does not converge. So let's assume that this series converges, and let's talk about the error term. So let's say you stop at term 3. Let's say you approximate an alternating series by stopping at term 3. What kind of error do you incur? Like, what kind of error do you have? You understand what I'm saying? Let me say that again. Assume that this converges, meaning that the summation from 0 to infinity of -1 to the n bn is equal to some value s. Now, we don't know what the value s is. We just know that it converges, so it's equal to some value s. Great. I want to approximate this value s. I want to find an estimation of this value s. So let's say I stop. So if we stop at term n. So let's say I take 5 terms, I take 100 terms, I take 10,000 terms, I take some number of terms. Then what is the error less than, right? So if we stop at term n, the error, my dear friends, the error is less than or equal to the term bn plus 1. So the error is always less than the first term you leave out. So this, technically, this is the term left out. Again, it's missing -1 to the n, right? So the first term that you leave out, but again, it's missing a -1 to the n because there's a -1 to the n here, and we're only looking at bn. So let me say this again. If you stop at term 5, the error is less than b6. If you stop at term 7, then the error is less than b8. If you stop at term 100, the error is less than b101. Furthermore, this is also plus something very, very important. If the next term is a plus, that means you found an underestimate. It means you need to add something to get to the value of the series. It means you're underestimating your series. And if your next term is a minus, that means you have to minus something to get to the value of your series. It means what you have is an overestimate. I realize this is a lot of information. Let me, say it in a different way. So, in a different way, let's write this as a note. Let's say that the summation from n equals 0 to infinity of -1 to the n bn, let's say that this converges. Right? So let's say that the summation from n equals 0 to infinity of -1 to the n bn is equal to some value s. Right? And let's say that we approximate, so we say the summation of n equals infinity, 0 to infinity of, let's say s is that sum. So s is approximately equal to b0 minus b1 plus b2. So let's say you stop at term B2. So this is, let's say, S2. So you stop at term 2. Right? So let's say you are approximating S by the sum, by like S2, by whatever, just call this something. So what does this mean? That means we are approximating S by B0 minus B1 plus B2. So we're stopping at terms 2. So we stop at n is equal to 2. What is the error less than or equal to? And is it an over or an underestimate? Right? So what's the error less than 2? If we stop at n equals to 2, then the error is less than B3. You stopped at N2, that means your error is less than B3. Now, is it an over or an underestimate? If you were to continue here, you would have to say minus B3, right? B is here. Right? It's that term in the series. Right, John? Your series is minus 1 to the n times Bn. So B is here. It's in the definition of the series. I will show you an example with a concrete B. So because you have to say minus B3, this means this would be an overestimate. Because you have to say minus B3, this is an overestimate. Because it's minus B3, so you're minusing that term. Okay, let me say this one more time. What's the common question that they ask you? I promise this will all make sense once we practice a full example. What's a common question that they ask you? They'll say, given a convergent alternating series, estimated with error less than or equal to some value. So they'll tell you, here is a convergent alternating series. How many terms should we get so the error is less than or equal to some value? So estimate it with an error less than or equal to some value. Here's how you solve this question. So the strategy is you find Bn such that you find n such that Bn is less than or equal to the error, and you stop before it. Let me give you an example, because all of this is all like words unless we practice an example. So here is the example that we're all waiting for. I will do definitely more than one example. So let's say you have part A, they ask you to find the Maclaurin series of the integral from 0 to 0.5 of tangent inverse x over x dx, which we've done already, right? We've done already. And part B is what we're going to focus on. They're going to estimate it. So they'll tell you estimate it, which is this is it, with error less than or equal to 0.005. 0.005. Okay, part A, we did it already. So part A, so this was done earlier. The integral of 0 to 0.5 of tangent inverse x over x dx. I'll do it very quickly. It's the integral from 0 to 0.5 of the summation n equals 0 to infinity of minus 1 to the n. It's x to the 2n plus 1 over 2n plus 1, but then we divide by x, so this is x to the 2n plus 1 all over 2n plus, so x to the 2n over 2n plus 1 dx. And when you integrate, this would be the summation from n equals 0 to infinity minus 1 to the n, x to the 2n plus 1 over 2n plus 1 times 2n plus 1 from 0 to 0.5. We did this earlier. Please review it. And this is the summation from n is equal 0 to infinity of minus 1 to the n, 0.5 to the 2n plus 1 all over 2n plus 1 squared. Please review this. It's very, very important. So, part B. We want to estimate this series. So we are told that this is a convergent alternating series. Now, to answer Jason, I think it was Jason questions earlier, what's Bn here? So this is an alternating series, right? How do I know that it's an alternating series? Because I have the minus 1 to the n. What is Bn here? Right? Bn is this, right? Isn't an alternating series a series that's minus 1 to the n times Bn? So when you tell me what Bn is, I tell you that Bn is 0.5 to the 2n plus 1 all over 2n plus 1 squared. Is this clear? Okay, and I want to say a comment, like a friendly comment, like please review series. It's not an easy topic. Students get confused about series all the time. Like when I teach series in my classes, students are confused a lot by it, and we have to repeat and repeat, and they have to practice a lot. So please, it's not a strange thing to look at this and feel overwhelmed or like this is not 100% clear. It's totally normal. With series, you have to practice a lot of questions. So this is an alternating series because it's minus 1 to the n times Bn. We want to estimate it to remember the typical question. Remember the common question that they ask us. They will ask us to estimate it with a certain error. So estimate it with an error less than this. The strategy that we do is we find the n such that Bn is less than the error, and then we stop before it. And I'm going to explain to you why. So we want to approximate this series with error less than or equal to 0.0005. So we want to find what n gives Bn less than or equal to 0.0005. And there's no magic trick here. You got to check it. So you try B0. B0 is 0.5 divided by 1. Definitely not less than this. What's B1? That's 0.5 to the 3 divided by 3 squared. I don't think that's less than. So let's take B2. It's 0.5 to the power 5 over 5 squared. Now let's try that. 0.5 to the power 5 divided by 25. That's 0.00125. That's still not less than. What is B3? It's 0.5 to the 7. I'm plugging them here, right? You understand where I'm plugging them. Divided by 49. This is 0.5 to the power 7 divided by 49, and this is equal to 0.000159, and here you go. I found the term that is less than or equal to 0.0005. Remember what I told you? You stop before it. So you stop at n is equal to 2. Let's discuss why do we stop at n is equal to 2. Because in alternating series, remember what we talked about. If you stop at term n, the error is less than bn plus 1. So here, if we say that the summation, or if we say that this is the integral from 0 to 0.5 of tangent inverse x over x dx, which is equal to the alternating series, minus 1 to the n, 0.5 to the 2n plus 1 over 2n plus 1 squared. So if I approximate it and I stop at n is equal to 2, so if I say when n is equal to 0, that's b0, so 0.5, well, b0, I have it right here. So it's 0.5 minus 0.5 cubed over 9 plus 0.5 to the power 5 over 25. So this is b0 minus b1 plus b2. So if I stop at n is equal to 2, right? If I stop at n is equal to 2, that means my error, this is the alternating series estimation error, is less than or equal to b3, and I found b3, which is 0.5 to the 7 over 49, and I chose b3 to be less than or equal to 0.0005, so my error is less than 0.005, right? I stop at term 2, so the error is less than b3, and I chose this, like I looked for b3, so that b3 is less than this. So theoretically, my error is less than b3, and I chose b3, so it's less than 0.05. I chose to stop at 2 because b3 is less than 0.005, so that's my estimation. Do we get this? So technically, guys, if I say that this is S2, now, is this an overestimate or is this an underestimate? Is this an overestimate or an underestimate? So next, I would have to say minus B3. So if I call this, let's call this for some reason S2. So let's call this, call it S2. I know that S2 is an overestimate because the next term would have been minus B3. So I'm minusing something to get to my series. So that means the value S, this is equal to S, right? Because this is a conversion series. So S minus S2, S2 is an overestimate. So technically S2 minus S is less than or equal to 0.0005. Because S2 is bigger. Do you understand what I'm saying? S2 is an overestimate. So if you wanted to do S minus S2, you would have to change this minus 0.005, right? Because if you want to change it around, it has to be minus. S2, I'm going to say this one more time. S2 is bigger than S because it's an overestimate because the next term is minus B3. You minus the next term to get to B3. Do you understand what I just did? Okay. Clearly, we need another example, right? Clearly, we need another example, and let's just go to a final. Let's say 2022. This is a Taylor approximation. These are integrals. I want a Maclaurin. Here we go. Consider the series. Okay, this is way too much. Use this series to show that. Error tests. Find the smallest and okay. So let's see. Let's do part A. I don't have the actual test without the solutions. I was only sent the test with solutions, so I'm trying to separate solutions from tests. So consider the series for the function arctan x, and notice how they gave you this. It looks a little bit different than the series I gave you, because the series I gave you starts at 0. I'm not sure why they chose to start at 1, but this is also a valid series. So they gave you this series. It looks different from our series because they chose to start theirs at 1. We chose ours at 0, but effectively they are the same series. Use this series to show that pi is equal to this. And notice how we say 4 times. So if you divide here, you get pi over 4. Well, take x is equal to 1. So arctangent of 1, which is equal to pi over 4, right? Arctangent of 1 is pi over 4, is the summation from n equals 1 to infinity of -1 to the n minus 1, x is equal to 1, 1 to the 2n minus 1 divided by 2n minus 1. So basically, take this and replace x by 1. So we're going to get pi over 4 is equal to, when n is equal to 1, this is equal to 1, right? So that's just 1. When n is equal to 1, we're going to get 1. When n is equal to 2, we're going to get 1/3. When n is equal to 3, we're going to get plus 1 over 5 minus 1 over 7 plus ... So if you want to find pi, then take 4 and multiply it by all this. That wasn't a terrible question. All you needed to see here is that to get to pi, right, to get to pi over 4, you just needed to replace x by 1 because arctangent of 1 is pi over 4. Okay, so let me go back and see what they want. Show that, to show that this series converges. See, they even say this is a problematic question. I don't understand. Let's do the error test. Okay, if the above tests are met, the error approximation of the event point is less than the absolute of the first submitted test. Yes, the result will allow you to write down. So here we go. This is part C. I don't know what they mean in part B, but let's see. Part C is the, we can check it later, or you can read these solutions later. Right now, I want to do the alternation. So find the smallest value n, right? Let's read this carefully. Find the smallest value n such that Sn minus pi, right? So they wrote the series as Sn like this. So basically, they wrote the series as pi equal to, look here. We wrote the series as pi is equal to multiply by 4 for the summation from n equals 1 to infinity of -1 to the n minus 1, all divided by 2n minus 1. This is what they're saying in this question. So The result in part B will allow you to write down a finite series of the form. Now they used Sn, so that means they stop at n. That means they stop at n. But if we, well, actually we could just keep it stop at n. But we can see that this is how do we get this series? Where are we getting that 4 from? That 4 is the 4 that's here, which is basically the 4 that's like here. Bigger
Recording
than
in
100.
progress.
Right? When you flip them, you change the inequality sign. So 2n is bigger than 101. That means, yeah, that means 2n is, sorry, n is bigger than 50.5. So for n is equal to 50, you're gonna get 1 over 99, which is not less than, well, actually, we'll do 51. For n is equal to 51, you're gonna get n is equal to 101, b 51 is equal to 1 over, sorry, there's a 4 times. I'm sorry, there's 4 times. I ate the 4. I apologize, I ate the 4. So this is 4 over 2n plus 1. I forgot this 4. Sorry, guys. So bn is 4 over this. I forgot the 4, I apologize. So that would be 2n minus 1. Sorry, let me redo this. So 2n minus 1 over 4 is bigger than 100. So 2n minus 1 is bigger than 400. So 2n is bigger than 401. So n is bigger than 401 divided by 2 is 200.5. So basically for n is equal to 201, b 201 is equal to 4 over 2 times 201, 2 times 201 minus 1 over 4 over 401, which is less than 0.01. Therefore, you stop at n is equal to 200. So you found the Bn that's less than 0.01. You stop before it. So you stop at n equals to 200. So find n. Well, n is equal to 200. So if you use 200 terms, the error will be less than 0.01. So if we stop at n is equal to 200, the error is less than or equal to b 201, which itself is less than 0.01, because that's how we found it right here. Do you understand what I'm saying? We find the term that is less than, we find Bn that's less than the wanted error, and then we stop before it. This is the alternating series approximation error. You find the term that is less than the error that they want, and then you stop before it. Am I making sense? Now here, is it gonna be an overestimate or an underestimate? So I'm doing like a little bit extra here. Is this an over or an underestimate? So you stopped at 200. Is this going to be an overestimate or an underestimate? And remember that pi is equal to the summation from n equals 1 to infinity minus 1 to the n minus 1, 4 over 2n minus 1. Please, please, please answer me this. If we stop at n equals to 200, right? So what is going to be, so if you take s of 200 minus pi, is this going to be positive or negative? Do we have, is this S200? So S200, is it an over or an underestimate? I want to give you a second. Over or underestimate? Well, what happens? You stopped at 200. So when you go to n equals 201, are you going to do plus or minus? So you have S of 200. So you stopped at term 200. If you want to go one more term, if you want to do the term n is equal to 201, are you going to get plus or minus? If you put 201 here, this is going to be plus, right? Because 201 minus 1 is positive. 4 over 2 times 201 minus 1. So the next term is a plus. So you're adding something to get to the series term. Therefore, S200 is an underestimate. Because you do for n is equal to 201, you do plus B201. So you do plus because the next term is positive. it means S200 is an underestimate, which means pi minus S200 is less than or equal to 0.01, right? That means pi is bigger. So you can put like here bigger than or equal to 0. If you want, you can say bigger than or equal to 0 because pi is bigger than S200. S200 is an underestimate. Am I making sense? It's basically two concepts for alternating series estimation. You find the Bn that's less than the error and you stop before it. And if the next term is plus, then it's an underestimate. If the next term is minus, then it's an overestimate. Really, it's just two things that we're recycling in different questions. Right? So the summary of things is this. So if you want an error less than or equal to A, what you do is then find n such that Bn is less than or equal to A, and then stop before it. Because if you stop before it, then the error is less than Bn, and Bn is less than or equal to A, so you achieve what you want. And the second topic is, if you stop, so if you stop at n, and next term is plus Bn plus 1, that means S of n is an underestimate, meaning S is bigger. S minus Sn is less than or equal to the error. And you can put a 0 over here if you want. And if you stop at n and the next term is minus Bn plus 1, so the next term is minus, that means Sn is an overestimate. For S, the value of the whole series, that means Sn minus S is less than or equal to error. And this is bigger than or equal to 0. So if you want S minus Sn, you got to make it minus the error here. So you got to put a minus on the error, and the 0 will go to the other side. This is basically the entire summary of the alternating series estimation test. Questions? Please, this takes practice. Let's say it one more time. This takes practice. Please, please, please. This is impossible without practice. Okay, let's see what they asked in 2021. See, it's the same story. Like, look, find the Maclaurin series of arctan x over x. Assume that this series satisfies the hypothesis. Then find how many terms to do when you want an error less than 10 to the minus 5. Do you see what I'm saying? Find the Maclaurin series of this, then estimate it to within 10 to the minus 5. So how many terms should you do to actually go to 10 to the minus 5? So if you want an error less than 10 to the minus 5. Let's look at the 2020 final. For the 2020 final, this is not series, not series, not series. Well, here, this is the series. So part C, you use Taylor inequality, and part C, they ask you to use alternating series. I did solve this in details, and I will share with you. This is the finding the ninth. This one we did, by the way. This one we did without telling you that we are doing it. So every single exam will have a question about alternating series somehow. Now, next topic is the Taylor polynomial and error bounds. So I'm going to do this on a new page. I'm going to do this before everybody gets tired. So Taylor polynomials and the error bound. And after I do this, I'm going to go back and I'm going to do more questions of error using Taylor or using alternating series. Because once we do this, we would have finished our series part. So I don't want to start multiple integrals heavy today. Maximum, I will do one or two quick examples of this, but I want to do the Taylor polynomial and error bounds before everybody gets tired. So the plan is I'm going to explain to you what this is. We're going to do one example of Taylor polynomial, then we're going to take our break, and then we're going to come back and we're going to do a whole hour of error terms with Taylor and then finding error terms with series. If we do enough examples and I feel that we're okay, then I maybe will start double integrals, but very, very lightly. I don't want to do any heavy integration today, and integration, I'm leaving it for tomorrow. Remember, all the midterm material is already posted for you in the pre-recorded part, right? So 2-3 minutes, and then we will take our next break. Let me just give you the actual definitions. So we know that a function f of x can be written as a Taylor series as the summation n equals 0 to infinity. Okay. F to the order n at a divided by n factorial x minus a to the power n. This is the Taylor series about x equals to a. We agreed that if we want the Taylor polynomial of degree n, so we stop at power n. So this would be the Taylor polynomial of degree n. So we stop at n. What's the use of Taylor polynomial? It's incredibly useful. I cannot tell you how useful this is. You don't do applications in it, but there's millions of applications for this. F of x is basically approximated by the Taylor polynomial of degree n at x. So you approximate f of x. F of x might be something very, very complicated. The Taylor polynomial is basically a polynomial of whatever degree you want. It could be degree 1, 2, 3, 5, 7, 18, 10 million, right? So f of x is approximated by the Taylor polynomial of degree n. Of course, if we stop at degree n, then there's a whole bunch of degrees that we're leaving out, right? If we stop at power 3, there's all the powers higher than 3 that we're ignoring. So that means there's an error, right? So if we stop at degree n, there is an error. There is en. Now, what is en? En of x. This is the upper bound on the error when we stop at degree n. So en. So when we stop at degree n, the enx is the maximum error that we incur. So the maximum error that we get, the maximum inaccuracy, if you want, is given to us by en, and en has a very famous formula. I'll tell you what these two bounds are. Fn plus 1 at x divided by n plus 1 factorial d to the power n plus 1. Now, there's a lot of things to talk about here. What is d? What is all that? So this is, first of all, let's talk about d. What is d? Right. You know that the center of convergence is a. Right. Since it's about x equals to a, that means a is the center of convergence. That's what we call a. It's the center of convergence. What's d? d is how far are you from a. So it's a theorem that your interval of convergence, you don't have to worry about this theorem, but it is a theorem, that your interval of convergence will always be centered at A. So you move a distance d to the side and you move the distance d to the side. Always, 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 the convergence of your series starts at A. Remember that A, the value here, the x minus A, and you go d to the other side. So your interval of convergence will always have the form A minus D and A plus D. So what is D? Again, please, what is D? D is how far is the estimation from the center of convergence. I will show you an example of this. It's not difficult at all, right? So let's say you have f of x at x equals to 1. So let's say f of x is equal to the summation x minus 1 to the power n. So that means a is equal to 1. And let's say you're finding f of 1.3, approximating it by T5 at 1.3. So let's say you're using the Taylor polynomial of degree 5 to approximate 1.3. What would D be? So if A is equal to 1, so your center of convergence is 1, you're using it to find f of 1.3, so you're moving 0.3 to get to that 1.3, right? So you're moving, so the point that you're using the estimation at is 1.3. The center of convergence is 1. That means D is equal to 0.3. It's how far are you from the center of convergence. So that's D. We're going to talk about it in a bit. Now, what do these two bounds mean? The two bounds mean this is the upper bound, meaning this, and again, it takes practice, it takes solving some questions to see it. This means, I'm going to put it in English. This is the maximum value that fn plus 1 of x can take. Now, the maximum value, positive or negative, maximum value in terms of size, right? Size. So we do not worry about negatives. So we're talking about the maximum, like the size. So if you can say get -7 or +3, you choose 7. You understand what I'm saying? We're talking size. So we don't care about plus or minus. So if you have the option between -7, 3, and 5, you choose 7, right? We don't care about the minus. 7 is the largest size that you can get. So the maximum value that fn plus 1 of x can take on the interval, of course, a minus d to a plus d, because that's the interval of our convergence. So again, it takes practice. It takes a lot of practice, not a lot, but it takes a few problems to be able to see how to do each one of those. And I'm definitely gonna practice that with you. So 2021 has a nice question. Let's look at it. Here we go. Here we go. So this is an example of oh, see, this even has alternating error. I love it. So this is going to be a review for both things. It's going to be a review for Taylor. So perfect. So we're going to do the absolute value of the error. So we're going to actually find this, and we're going to find this, and we're going to find the error. Then we're going to do the alternating series error, and then we're going to do Taylor's inequality error, and we're going to see which one is the best. Right? So I say let's just take a small break now before things get overwhelming, because I know students don't like this very much. So let's take our break right now. And then when we come back, we'll do an hour of this, more alternating, and then whatever questions you have, and then maybe we could do an extra topic of maybe we can introduce multiple integrals before tomorrow. I don't like to start multiple integrals today because maybe somebody's not here today and they show up tomorrow and we've already started like double integrals and we're going to start in the middle of double integrals, then that somebody will be lost, right? And the video of today won't be made available, I think, before tomorrow's session. I hope so, but just in case they're late and they posted at like 6 and not, not 3:30 or something, or maybe you can't watch it tomorrow before like they post, like maybe they posted early but you don't have time to watch it and somebody shows up and we're starting in the middle of integration. I don't want them to feel lost the whole session, so I try and